In this video, we are going to create a Sudoku solver in Java. It's going to be a full tutorial. We're going to start from scratch and show the full process. We're going to walk through the code in a way that is easy to understand so you'll be able to write it yourself. My name's John and I do a new Java tutorial video every single week. So be sure to hit the subscribe button so you don't miss each week's video. I also have a full Java course available in the link down in the description if you're interested. As always, the full source code for this program is available in the link down in the description, so go and get it. If you're watching this video, you're probably already familiar with the rules of Sudoku, but just in case, let's go over them very quickly. What you have is a 9x9 grid of numbers split out into 9 3x3 squares. The goal is to fill out the grid with numbers following some simple rules. The rules are just that each row, each column, and each 3x3 square must contain all numbers between 1 through 9. Basically what that amounts to is you can't have the same number twice in any given row, column, or 3x3 square. First of all, the game board that we're going to start with, the grid, we're going to use a two-dimensional int array. So that's just int double array, and we'll just call it board equals, and this is the only part I'm going to paste in because I don't feel like typing it all out. But this is the syntax you're going to want to use. It's a two-dimensional array, and with this layout, you can kind of see what the board looks like. And this board layout is just from a Sudoku game generator that I found online. So as you can see at the top, we have like 7, blank 2, blank 5, etc. That corresponds to over here we have 7, 0, 2, 0, 5. Here, since we have a 2D array of ints, we have to use some number here. So we'll just use zeros as the placeholder for blanks. So now we have our starting Sudoku board. Another thing that we're going to need many times in the algorithm that we write is just the size of the grid. So in this case, we have a 9x9 grid. So we're going to need that length of 9 in a lot of places. So let's just create a constant for that. So that'll just be a private static final int grid size equals 9. The next thing that we're going to need is some helper methods. When we place a number, in order to see if it's a valid placement, we're going to have to see if that number already appears in that row, that column, or that 3x3 square. And if it does, we can't place that number there. So to do that, we're going to need 3 helper methods for whether that number already exists in the row, column, or 3x3 square. So let's just start with the first one for seeing if that number already exists in the row. So we'll just have a private static Boolean. This is a Boolean so we can return true if that number already exists in the row and false if it doesn't. Is number in row. And we're going to need to take in a few parameters. The first one is the board itself. So an int two-dimensional array called board. And next, an int for the number that we want to check is in the row. And then one more int for the row number itself. Technically in this case 0 through 8 because we're going to be dealing with array indexes. So for this we're going to want to create a for loop for int I equals 0, I less than the grid size, which of course is 9, I plus plus. What we'll do is say if the board in that row that was passed in at the current column of I that we're iterating through, if we find that number that we're checking, then we want to return true. And if we get through that whole for loop and never find the number, we know we can return false because we did not find that number in the row. So that should do it for our isNumberInRow method. Now let's create a similar method for isNumberInColumn. So we still want a few parameters. We want the board, that stays the same. We want the number that we're looking for in that column, that stays the same. But of course, instead of taking in the row as a parameter, we're going to take in the column that we're looking at as a parameter. And a lot of this method does stay the same that we copied from the row method. But instead of looking at the board at row and column I, we're going to be looking at the board at row I and column. For example, if we pass in 0 as the column, it's going to look at the board at position 0, 0, 1, 0, 2, 0, 3, 0, etc., all the way up to 8, 0, to check if that number exists anywhere else in that column. And if we do find it, again, we return true. And if we loop through that whole column and don't find it, we know we can return false. That number does not exist in that column. So those two methods are relatively simple, but the method for checking whether that number exists elsewhere in that 3x3 box is a bit more complicated. But again, we'll start with a copy of the column method and make our modifications. We'll just call this isNumberInBox. Of course, we want to take in the board, we want to take in the number that we're looking for. But instead of just taking in the column or the row, we're actually going to take in both so we can get the exact coordinates of the number that was passed in. So we'll just add int row here. This one's a little tougher to visualize how we're going to do it, but let me see if I can make it make sense. For example, let's say we need to check if we can add the value 1 to this spot here. You know, we already have the code that checks the row or the column. We see that 1 doesn't exist there. So we need to check this local 3x3 box. So the method is going to get passed in the coordinates of this box that we're looking at. And in that case, that would be row 1, 0, 1. So the row would be 1. And the column would be 0, 1, 2, 3, 4. So it would pass in 1 for the row and 4 for the column. What we want to do is get the coordinates of the top left corner of that local 3x3 box so that we can easily traverse that 3x3 box to check if that number already exists anywhere in there. But that part is the part that is a little bit tricky. How do we do that? So we're actually going to need a couple of variables. So let's create an int. Let's call it local box row. For example, here we come in with a row of 1, but we want to start at this position here. So we need to get the row of this position. How do we do that? Well, what we can do is take the row that's passed in and then subtract row mod 3. So mods, if you're not familiar, takes the first number and divides it by the second number and gives you the remainder. So in our example, we have a row of 1 divided by 3 is 0 with a remainder of 1. So what we get for our example is 1 minus 1, and our local box row will be 0, which is exactly what we're looking for. Same thing for the column. Int local box column equals column minus column mod 3. Again, in our example, the column that was passed in was 4. So that would evaluate to 4 minus 4 mod 3, which is 1. 4 minus 1, so the local box column will have the value 3. So our local box row and column will be 0, 3. So the 0th row is this first row here, and the 4th column, 1, 2, 3, 4. So that successfully gave us the location of the top left corner of the 3x3 box we were looking at. And this little formula works for any box in the grid. All right, so now that we have that top left location, how do we use it? Well, we need to do a clever little nested for loop. We'll say for int I equals local box row, go while I is less than local box row plus 3, I plus plus. So that iterates through the 3 rows in that grid. And the same thing for the columns. So we'll do for int j equals local box column, j less than local box column plus 3, j plus plus. So this will loop us through that exact 3x3 grid that we want to. And then we want to do basically the same thing we did before, where we want to check if the board at row I and column j, if that spot matches the number that we're looking for. If we find it, we return true. And if we get through this entire nested for loop and never find it, we know it's not in that 3x3 box, so we can return false. All right, so now we have our 3 checks for whether the number is in the row, in the column, or in the 3x3 box. For convenience, when we're writing our algorithm, let's write one method that checks all 3 of those. So we can just call it to see if a certain placement is valid. So we'll have another private static boolean is valid placement. And for that, we'll need to take in the board again, of course, the number that we're going to put in that spot, and the coordinates where we want to put it. So int row and int column. Basically here we just need to call those 3 methods, and if they all return false, then we know this is a valid placement. So we can just say return not is number in row, and we need to pass in the board, the number that we're looking for, and the row, and not is number in column, pass in the board, the number, and the column, and not is number in box, where we pass in the board, the number, the row, and the column. Okay, now with all of those methods in place, we can get to the real meat of the algorithm here. That's going to be the method that does all the recursion and the backtracking and all the magic that makes this Sudoku solver work. Let's quickly talk about how the algorithm we're going to use works. If you've ever played this yourself, it's going to be very different from how a human would play it, but for a computer, it works great. This is the start state of our board, right? What we're going to do is traverse the board row by row, and for each square, what we're going to do is, if it doesn't already have a number in it, for that cell, we're going to look at all the numbers between 1 and 9, and check whether each of them is valid to add in this space. So for the second spot, for example, between the 7 and the 2, we're going to loop through the numbers 1 through 9 until we find a value that is valid for this cell. So can we set this value to 1? Well, no, because 1 is already here in this 3x3 grid. Can we set it to 2? No, same reason, 2 is already present in the 3x3 grid. Can we set it to 3? Yes. 3 isn't anywhere else in this row, it isn't anywhere else in this column, and it's nowhere else in this 3x3 grid. So we set this value to 3 and move on. And the process will start over recursively from the beginning. We loop through the whole grid until we find a value that is not populated yet, and it finds this first empty cell. And it says, okay, is the number 1 valid in this space? And yes, it is, because it doesn't appear anywhere in the row, column, or 3x3 square. So you might be thinking, what happens if we go through each of the numbers between 1 and 9 in a given square and none of them are valid? Well, that's where the backtracking comes in. So let's say for example, we are evaluating this square here, and we went through all the numbers 1 through 9, and none of them are valid. They're all present somewhere in the column, the row, or the 3x3 grid. Well, what we do is we backtrack back to the last number that we set. in this case this 3 here. And since this number being 3 didn't result in us being able to solve the board, we clear that out and keep trying all the rest of the numbers in that spot between 1 and 9. So can we put a 5 here? No, it's in the row. A 6 is also in the row. A 7 is in the grid. But an 8 is valid in this spot. So we set the cell to 8 and move on again. And the next iteration would again traverse this whole grid until it finds a blank spot. And in the first blank spot it encounters, it tries all numbers between 1 through 9. And it keeps going through this process over and over again until it fills out the entire grid with valid moves. So for that, let's create a new method. We're going to have a private static. Again, it'll return a Boolean, and we'll just call it solve board. And it'll take in as a parameter just the 2D int array board. So to get started, we are going to have a nested for loop so that we can loop through the entire grid. So it's just for int row equals 0, while the row is less than the grid size, which would be 9, of course, row plus plus, and nested inside that for int column equals 0, column also less than grid size, column plus plus. Since we're using zeros for the blanks, this is a representation of the board, kind of how the computer sees it. So when we loop through this grid, what we're looking for is a space that hasn't been set yet. So in our case, a blank is a 0. So we just want to say if the board at that row and column is equal to 0, we are going to do some stuff. What does our algorithm say that we do when we encounter a blank? Well, what we do is we start trying every number between 1 through 9 and see if it's valid. So let's write the code that loops through all the numbers between 1 through 9 and tries all of them. That'll just be another nested for loop. Yes, there are a lot of nested for loops in this algorithm. Int number to try, because it's the number that we're currently trying in this spot. We're going to start it at 1, and we're going to go while that number to try is less than or equal to that grid size, which is 9. Number to try plus plus. So we're looping through every number between 1 and 9 for this spot, and we have to check each of those to see if that number in that place is valid. Luckily, we have this nice convenient isValid placement method to do that. So we can just say if isValid placement. We need to pass in the board, the number we're trying, the current row that we're looking at, and the current column that we're looking at. And if that is a valid placement, we place the number there. To do that, we just say board, at that row, at that column, set that equal to the number that we're trying. And of course, if the first number it tries isn't a valid placement, it just goes to the next one. So now that we've placed this number that we're trying in this spot, this is where the recursion of this algorithm comes in. And recursion is sometimes weird to understand, but bear with me. What we need to do is call this solve board method recursively here, passing in that same board. So it'll go through all of this code again when it's called recursively. So let's talk through an example to see what exactly is happening. So let's pretend in this second spot here, we tried 1, it was invalid. We tried 2, it was invalid. We tried 3 and said, okay, it's valid. That's here in this code. We saw that it was a valid placement, and so we set the number 3 in that spot. So we've set this number 3, and then we recursively call our solve board method. And what it's going to do is, again, traverse the entire grid, finding the first blank spot. So now it skips these because they've already been set, and the first blank spot that it finds is here. And it does the same thing it did before. It tries every number between 1 through 9 to see if it's valid. First it tries 1, and that's not in the row, it's not in the column, it's not in the square. So this is a valid placement. So again, it'll recursively call that solve board method and do the same thing over and over again, filling out this whole grid. But it won't work yet with exactly what we have here. What happens if we're checking a given spot and we go through all the numbers in this for loop here, 1 through 9, and none of them are valid? Well, what we actually want to do in that situation is return false. Returning false here pretty much just means I can't solve this board. It was unable to put a valid number in a certain spot. On top of that here though, where we're recursively calling this solve board method, we need to say if that recursive solve board call returns true, so just if solve board, then we want to return true here. So basically, if we tried this number at this spot, and then the recursive call to solve board succeeded, which means that all the recursive calls beyond that also succeeded and bubbled back up, then we can return true here too. This placement resulted in the whole rest of the grid being filled out successfully in the recursive calls. But if it didn't, and this recursive solve board call returned false, we want to have an else here that actually clears out this placement that we tried. So board at row and column, we want to set back to 0. So let's think about what that is actually doing. We found that a certain number at a certain spot was valid, and we tried placing it there. And then we tried to solve the rest of the board and discovered that there was no way it could do it. It couldn't figure out how to solve the rest of the board with this number that it was trying. So that means that this number that we were trying doesn't actually work. Even though it's valid here right now, we can't solve the rest of the board with this number set in this position. So we clear it out and set it back to 0, and then it just goes through the next iteration of this for loop here and tries another number. There's one last little thing we need in this method, and that is at the very end. If it gets through this outer for loop completely, then we do want to go ahead and return true. If you're struggling to understand exactly how this algorithm is working, trust me when I say it is not just you. If you're new at all to recursion, or especially if you're new to Java in general, this kind of algorithm with the complexity that we're looking at can take a while to sink in. So just give yourself some time to allow that to happen. Work through it in your head, look at the code, walk through parts of it step by step, and after a while it'll become clear to you how this is working. All of this crazy looking logic that we added in here, it gives it the ability to basically walk through this entire grid, trying out each number in each spot. But if eventually it runs into a situation where it can't successfully place any valid numbers in a spot, it allows it to backtrack and try different numbers in previous spots. And it'll keep going, backtracking whenever it has to perhaps change numbers that it set before that resulted in it being impossible to solve. But eventually, if you start with a valid, solvable board, this will come up with a solution, and it'll do so very quickly. Now that we've created this giant monster of a complex method, we aren't calling it anywhere yet. So let's go back to our main method and call that method to solve this board. So we can just say if solve board. If that solve board method returns true, then we know that that board was successfully solved. So we can just print out system.out.println solved successfully. And if not, it's most likely because the board that was entered wasn't a valid board in the first place. There are some combinations of numbers that you can put on a starting board where it's actually impossible to come up with a solution. So we can just say system.out.println unsolvable board set base. But now after this runs, we should have a solved board, but we aren't printing it out anywhere, so we have to actually print it out to prove that we've solved the board. So let's just whip up a quick method to print the board. We pass in our board, and we're going to use the helpful stuff in Eclipse to automatically create this method that doesn't exist yet. And it gives us this auto-generated method stub. So here again, we'll just do a nested for loop for int row equals 0, row less than the grid size, row plus plus. Same for the columns, int column equals 0, column less than grid size, column plus plus. We're going to do system.out.print, not print line, the board at that row and column. And then also after each row, we want to print a new line so we aren't just printing out all the numbers on one giant line. So system.out.print line. We don't even need any parameters here. We just want the new line, and print line with no parameters gives us that. So now the moment of truth, let's run this program and see if it solves this Sudoku board. Here we go. Okay, solved successfully. And it looks like they are all correct. Awesome. One more thing though, this printout kind of stinks. It's not laid out in the nice Sudoku way. It doesn't have all the lines and everything. It's fine, but it's just not up to my standards yet. So what I want it printed out like is like this, where we have the lines between each subgrid. Basically what we want to do is, after every third row, we want to put in this line of hyphens to get this line here and here. And after every third column, we want to put in one of these pipes, one of these vertical bars. So first let's deal with these horizontal lines after every 3 rows. So back in our printboard method, just inside this first for loop, we'll say if row mod 3 equals 0, so for every third row, and the row is not equal to 0. If we don't include this part here, it'll also put a row of hyphens at the very top before the first row, and we don't want that. So for every third row, except for that very top one, we just want to do system.out.println. Basically, we want a whole bunch of hyphens and a new line. So how many do we need here? Looks like 11 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, let's go ahead and run that and make sure that part of the printout looks good, and it does. Now let's go ahead and do the same thing with the columns where we put that pipe character between every third column. So it'll look very similar. We'll just say if the column mod 3 equals 0 and column not equals 0, because again, we don't want the pipe before that first column, we just want it in between those other sections. Do system.out.print that pipe character. Run it again and see how it looks. Beautiful. So right now we're just printing out the board at the very end. I think it would be really cool if we could print out the board at the beginning too, before we solve it, so we could see the before and after. That's really easy to do. We just go up here before we call the solve board method and call our print board method, so we're printing it out before it's being solved. Run it again and we should see the before and after. And we do. That is pretty awesome. Pretty neat, right? I think this algorithm is really interesting. If you ever played Sudoku yourself before in the newspaper or on your phone or whatever, you would never think about solving a Sudoku board like this. It would be an absolute nightmare. You do it a completely different way doing it as a human. But as a computer that can try out just billions of numbers super fast, this makes total sense. It is really easy for a computer to do. It can absolutely take some time to understand exactly how it is working, but just give yourself some time to do that. Follow along and write out the code yourself, or go to the link down in the description to download the full source so you don't have to type it out, and just take some time to walk through it and play around with it. And go online to a Sudoku generator, plug in the appropriate values here to the board, and see how it works. If you did enjoy this video or learn something, please let me know with a like, and be sure to hit that subscribe button so you don't miss each week's video. And I really do appreciate you taking the time to like and subscribe. It's the only way these videos get out to help more people, and so I really do appreciate that. Thank you so much for watching. I will see you next time.